Okay, so today we're going to start chapter 3. So we're still in the second unit. So the chapter 2 was all about polynomials, and we learned things about end behavior in polynomials, zeros of polynomials, what their graphs look like. And so now we're going to look at a new family of functions, rational functions. And the root word here of rational is ratio. A rational function is a ratio of polynomial functions. So technically speaking, if I set the denominator here equal to 1, all polynomials are contained in this larger family of functions, rational functions. But what happens with rational functions is now that you've introduced a denominator, you may accidentally try to divide by 0. So let's talk a little bit about division by 0. And this is the same talk I give my calculus students on the first day of class. So in this chapter, we sort of dip our toes into calculus, all right? Because calculus, part of something that happens with calculus is we're trying to resolve what happens when you try to divide by 0. Okay, so let's talk about that. Division by 0. All right. We know we're not supposed to do it, but why not? And there's two sort of different flavors of dividing by 0. So let's talk about one way to think about division. If I say I want to figure out 6 divided by 2, one way to think about that is we're trying to figure out what times 2 gives you 6. So that would be 3. And we can check our answer here by looking at 3 times 2. And indeed, that's 6. So this is what's called the missing factor approach to division. And so if we try to divide 6 divided by 0, let's call that x. Then what would have to happen is that x times 0 would have to be 6. But here's the problem with that. We know that any number times 0 is 0, and that's never going to equal 6. So 6 divided by 0 is undefined. So this is undefined because we can't. There's no possible answers. And so that's one sort of classification, if you will, of division by 0. Is if you have a non-zero number over 0, and that just plain isn't fixable. Okay, I noticed something here. Okay, so that isn't fixable, and we're going to see what that means graphically here in a minute. Now let's look at the other case of division by 0 is what if you want to do 0 divided by 0? So if we kind of proceed the same way, let's call that number x. Then that would mean that x times 0 would have to be 0. And the good news is this happens all the time. Okay, so when you have 0 divided by 0, it's undefined because any number works. And so that's the second kind of division by 0 we're going to be seeing here today, this week. 0 divided by 0, that can pretty much be anything. And as I mentioned it before, once again, division by 0, in particular 0 divided by 0, is the problem that calculus seeks to address. If you go on take calculus, a lot of folks are very intimidated by calculus. If you look at a calculus book, there's all sorts of symbols in there. Don't let that put you off. most of calculus ends up being just algebra and well, depending what calculus go into, algebra and or trigonometry. So that's my little spiel on division by zero. So what we're going to look at today, we'll look at a couple of functions, and we're going to look at behaviors here. So something that becomes an issue with rational functions is when the denominator is 0, right? We can't have that. We need to exclude these values. So when we talk about excluding values or values excluded from the domain, we're looking at setting the denominator equal to 0 and then throwing out our answers. Okay? So let's take a look at this function, f of x, 2x squared minus 3x minus 2. Divided by x squared minus 4. And the first thing we want to do when looking at a rational function is we want to find the values excluded from the domain. Remember that the domain here is a set of allowable inputs. In this case, the inputs are the x's. And so, looking at this, we can't divide by 0. So the strategy here is solve where the denominator is equal to 0 and exclude the answers. Okay, so here our denominator here is x squared minus 4. We set that equal to 0. We can factor, we can quadratic formula. We can add 4 to both sides and extract square roots. So there's, a few different ways to handle this problem. But at the end, we get the plus and the minus 2. And so if you're going to extract the square root to solve one of these basic quadratics, don't forget the plus or the minus. All right? It's just one of those things students tend to forget about. Not just in college algebra, but pretty much in all the courses. Now, what we found here is we found the x values that are going to cause division by 0. Okay, so these are the x values that are going to cause trouble. So we need to exclude these from the domain. So our domain would be all real numbers except plus or minus 2. And the way we would write that using our interval notation is we have our minus infinity to infinity. We'd have the negative 2 and 2, and we would exclude those values. So that means we would have open circles above there, but we can be anything besides those. And so our final answer here for domain with interval notation would be your minus infinity to negative 2, union negative 2 to 2, union 2 to infinity. And that's always going to be the first step in analyzing a rational function, is you want to look at the domain, find the values that are going to cause trouble. All right, so we know at 2 and negative 2, We know at 2 and negative 2, the denominator will be 0. Let's see what sort of division by 0 do we have at those values. Do we have a non-zero number over 0 or a 0 over 0? And then we're going to look at the graph and see what's happening on the graph. So let's investigate where we're not supposed to go. We'll investigate negative 2 and 2. So I'm just going to put the function down here for reference because my memory is terrible. All right, so let's plug in the negative 2 and see what happens. Or let's attempt to plug in the negative 2, we should say. We know the denominator works out to 0. Let's look at the numerator. I've got a negative 2 squared, which is a positive 4, times 2, which is 8, minus 3 times negative 2, which is minus a negative 6, which would be plus 6, minus 2. So what we've got here is we've got a 12 over 0. Okay, so we have a non-zero number over 0. And so, you know, this is, we're going to see what happens on the graph with this. Let's try f of 2 and see what happens in this case. So now I'm going to get got my 8 minus 6 minus 2 over 0, and this is a 0 over 0. Okay? So remember, non-zero number over 0, there's just flat out no solution to this one. This can be anything. All right? So we got those two different sorts of things happening when I plug in to a negative 2. Now, once again, technically, I'm not allowed to plug in those things. Algebra is very upset with me at this point. All right, because I'm trying to divide by 0. So let's head on over to Desmos and see what's happening graphically. So we've got two different algebraic behaviors. Let's look at the graphical behaviors. Try to, if I can get this. All right, I guess it is what it is. So let's sneak our f of x in here. Equals, we're going to have a fraction. We've got 2x squared minus 3x minus 2 over x squared minus 4. And let's take a look here. Near x equals negative 2. So if I zoom out a little bit, you can see the graph is torn when x is negative 2. And I can make that more explicit. If I type in x equals negative 2, that's going to be a vertical line. I'm going to make it a dashed line. And you can see the function is really trying, it's really getting close to that vertical line. Now, because our graph is a function, or because f is a function, its graph can't actually become the vertical line, because then it would fail the vertical line test. But it's becoming very close to a vertical line. And so this kind of behavior we call asymptotic behavior. So the word asymptote is, it's a line that the function is trying to emulate, is trying to become the line. In this case, we have what's called a vertical asymptote. Because we have a vertical line, x equals negative 2. All right, so at x equals negative 2, the function is trying to become that vertical line, so it's called a vertical asymptote. But we can actually then describe what's happening near x equals negative 2. So near x equals negative 2. So this is kind of, like I said, we're dipping our toes into calculus. This is the kind of thing calculus talks about. So you see I've got two different behaviors here. I've got the graph shooting up towards infinity, and I've got the graph shooting down towards negative infinity. And so we want to represent that somehow. And so this is how we can do it. You notice that as I'm coming into -2 from this direction, from the left, the function values are heading up to infinity. So the way we write that down, the way we codify that, is we say as x approaches -2 with a little minus up here, f of x approaches infinity. Now we've seen this kind of thing before with end behavior on polynomials. So let's talk about this notation. So x arrow -2 with a minus is x approaches -2 from the left. So that little minus sign up there means from the left. Because we're thinking of x at this point as being -2 minus a little bit. So -2 minus a little bit puts you a little bit to the left of -2, and that means we're coming into -2 this way. And if you can approach -2 from the left, we're going to approach -2 from the right. As x approaches -2 from the right, we'll have a little plus. The f of x, the y values are going to head down to negative infinity. So x approaches -2 from the, with that little plus means x approaches -2 from the right, meaning x equals -2 plus a little bit. Okay. And this is more precisely defined in calculus, but we have the tools, we have the graphical tools here to kind of see what's happening. So that's what a vertical asymptote is. A vertical asymptote is a tear in the graph at a finite value, in this case x equals -2, the graph is trying to blow up to infinity. Okay, the y values are getting outrageously large. Now we'll see applications of this kind of behavior in the real world. One of the classic applications of this is the old adage, you can't go the speed of light, right? You cannot go the speed of light because that would take infinite energy. Okay. There's one example we do where we're looking at trying to remove a certain amount of pollutant from a river. To try to get 100% the river 100% clean would end up costing infinite money. Okay, so there are practical applications of this sort of behavior. Any questions on the notation there? Coming from the left, coming from the right. We'll do more examples, of course. But -2 from the left, think of -2 minus a little bit. That puts you a little bit to the left of -2. -2 from the right, -2 plus a little bit. All right, so that's what's going on at -2. Let's check out what's happening near +2. So let's zoom in here towards +2. Let's get over here. Here's the graph near +2. Notice it looks perfectly fine. So if I click on here and I move over, as I get close to 2, I mean, the y values seem perfectly behaved. The graph is not torn up at all. In fact, if you look at those y values, they seem to be getting close to 1.25. Right? Now at 2 itself, of course, we have a hole in the graph. Right? So we have a hole in the graph. You remember the hole in the graph from chapter 1 means the function isn't defined there. So what's happening in this particular case is we have a hole at x equals 2. And to kind of look around that a little more precisely, let's add a table in here. So click Add Table. And I guess we'll add it down here. See what's happening. So we'll have the x1 there. We can highlight that and just type f of x1. And of course, if you plug in 2 itself, it's undefined. All right. So let's plug in values getting close to 2. Once again, we can get close to 2 in 2 different ways. We can come in this way. X approaches 2 from the left. And we can come in this way. X approaches 2 from the right. So for x coming into 2 from the left, we're looking at x equals 2 minus a little bit. And for x approaching 2 from the right, we can think of x as being 2 plus a little bit. So we can do that here on the table. If we think of x, a number a little bit less than x, we can, a little bit less than 2, we can think of something like 1.9 or 1.99 or 1.999. Okay? And here's what's nice about the table function here in Desmos is you just start putting in 1.9. It'll calculate that. It'll put the point on the graph for you. Let's zoom in a little bit. And we can just keep adding 9. So watch what's happening to the f of x value. Remember, those are the y values. So that number, the y values, are getting closer and closer to what appears to be 1.25. Okay. Now we'll actually use algebra to prove that it's going to 1.25 here in just a second. And I can do the same thing with something a little bit bigger than 2, like 2.1. If I wanted to get closer to 2, I could just put 2.01, 2.001, etc. And notice those function values appear to be getting closer and closer to 1.25. So the numbers suggests so the data suggest we have a hole at 2 comma 1.25. Okay, but the question is, how can we prove that? Okay, remember, technology will suggest things. It's the math that actually proves it. So let's take a look at that function again. And remember, this function is an algebraic fraction. So let's talk about regular fractions. Like if you had a regular fraction, you kind of have 2 types of fractions. You've got fractions like 5/3 and fractions like 12 over 28. So this fraction is called lowest terms because the numerator and denominator have no common factors. Remember, a fraction is really talking about dividing 2 numbers. This fraction, however, is not in lowest terms because there are common factors in the numerator and the denominator. So I can, in the numerator, I've got 4 times 3. The denominator, I've got 4 times 7. And since we're dividing here, we're multiplying by 3 and then turning right around and dividing, we're multiplying by 4 and then turning right around and dividing by 4, right? That cancels out to 1, and now we get 3/7. Okay? And so to get to lowest terms, we need to factor numerator and denominator. And then we cancel out common factors. Okay? That's how you reduce a fraction, whether it be a numerical fraction or an algebraic fraction. Now, we just spent an entire chapter, chapter 2, talking about factoring polynomials. So that's going to pay dividends here. Most of the examples we're going to do, to be honest, we'll be able to factor using the stuff you learned from the previous classes. But there are a couple examples where you're going to have to dig in, and you may need to pull out some synthetic division now and then. But let's try that here to see what's going on. The denominator is a difference of squares. So that factors nicely for us. Let's look at the numerator. If we're trying to unfoil this, we need to split that 2x and x. Then we can guess here minus 2 plus 1. We know that when we plug in 2, we get a 0 in the numerator and a 0 in the denominator. So the factor theorem guarantees there's going to be a factor of x minus 2 there, you follow. And so that common factor cancel out. This is what's causing the 0 in the numerator. This is the factor causing 0 in the denominator. And what we find is we can reduce the function down. So long as x is not 2. We can cancel x minus 2 over x minus 2. So we reduce the formula. The reduced formula for the function, 2x plus 1 over x plus 2. And this is good as long as, we're not trying to plug 2 in. That being said, if x gets close to 2, then 2x plus 1 over x plus 2, well, that numerator is going to get really close to 2 times 2 plus 1 over 2 plus 2, which is 5/4, and sure enough, that's 1.25. So this is how we algebraically know that there's a hole in the graph at 2, 5/4. So we're locating the hole in the graph here the same way we located holes in the graph in chapter 1. In chapter 1, we'd have a piecewise function usually, and we would plug the point in where it wasn't equal to, and then we could just put a hole there instead of a dot in the graph or a point on the graph, and that's the same thing that's happening here. Okay, so let's do another example. So once again, anything that, like for example here, these are two problems. Find the values excluded from the domain, write the domain using interval notation, and use a graphing utility, so either Desmos or a calculator, to examine the behavior. Okay. Once again, the answer key to this is on Blackboard as well. So I'll leave that to you if you want to do that. We're going to be doing so many of these types of things that I'll leave that to you to do. Normally that would be something you'd work on together in class. So let's look at this example here, x squared minus 4 over x squared plus x plus 2. So let's try to put the ideas we've kind of discovered here into practice. The first thing we're asked to do is find the values excluded from the domain of f. So once again, what's going to get us in trouble is if we try to divide by 0. So we're going to set that denominator equal to 0. It's a quadratic. We attempt to factor. If we didn't factor, we could always run it through quadratic formula. And now we set each factor equal to 0. I get x equals 1 or x equals -2. And so either of these are going to cause issue in the denominator. So those are my excluded values. 1 or -2. I'll put the -2 first since that's the smaller of the two. Now it asks to write the domain using interval notation. So in interval notation, we start off with the real number line. And these are the excluded values. So those are the values that we're not allowed to have. So we got to exclude those, but I can have anything else. And so my domain would be -∞ to -2, using -2, union -2 to 1, union 1 to infinity. Any questions on why the values are excluded and how we find they're excluded? So now it says use a graphing utility to help you describe the behavior of f near the excluded values. So we're going to dial this into Desmos. So we got the x squared plus 4 on the numerator now. We got the x squared plus x minus 2. And let's zoom this back to a standard kind of window here, -5 to 5. -5 to 5. And what do we see here? Our two excluded values were -2 and 1. So looking here at -2, everything looks cool at -2. So we suspect that there's a hole here at -2 comma something. And what's happening here at 1? It's torn up. So we would call this a vertical asymptote at x equals 1. So the vertical asymptote we can see here pretty clearly as x approaches 1 from the left. So as I'm coming in to 1 from this direction, the graph is heading up to positive infinity. And as x approaches 1 from the right, the f of x is heading to negative infinity. So that describes the behavior there. We have a vertical asymptote at 1, but this, what we wrote down here, describes better what's happening near 1. Now to figure out what the hole in the graph is, that's a little more involved. That's coming from a 0 over 0. So when you have a hole in the graph, it's because the 0 over 0, that cancels out to some number. And so we can figure out what that is by reducing the function to lowest term. So the numerator, we already know how that factors from the last example. The denominator, how's that going to factor? X plus 2, x minus 1. Sure enough, the x plus 2 cancels from numerator and denominator. And so I reduce this down to x minus 2 over x minus 1. And as x gets close to -2, plug that -2 in. This is getting close to a -4 over a -3, which reduces to 4/3. So when we do an analysis here, we should see the y values there getting close to 4/3. Now as a decimal, 4/3 is 1.3 repeating. So we can confirm our answer there by making a table. But before we do all that, are there any questions over what we're getting here from the graphing utility and then the algebra to back it up? All right, so let's make a little table here to check what's going on near -2 to see if the 4/3 if that tracks. So we're going to write f of x1 there, and we need to look at -2 from the left and coming into -2 from the right. So as x comes into -2 from the left, remember we're thinking about x being -2 minus a little bit. X coming into -2 from the right means we're looking at x being -2 plus a little bit. So -2 minus a little bit, those are going to be numbers like -2.1, -2.01, etc. -2 plus a little bit would be things like -1.9, -1.99, etc. Okay. So once again, we want to make this table to check that the 4/3 we got from the algebra makes sense. Okay, so we're just checking that by plugging in these values. So if I do like -2.1, 01, you can see it's getting closer and closer to 1.3 repeating. And the same thing on the other side as I plug in those 9s. You can see it's getting closer and closer to 1.3 repeating. Okay, so that checks that the whole is at -2 comma 4/3, -2 comma 1.3 repeating. Okay. And so we did that already. We reduced the function down to find the exact location of the hole. So here's the general methodology, general theorem here. In general, at excluded values, the graph of a rational function has either a vertical asymptote or a hole in the graph. Holes in the graph comes from factors canceling from the denominator. So if you have a 0 in the denominator, that means there's a factor creating that 0. If you have the factor in the numerator around that cancels it out, that's going to produce a hole in the graph. So if the graph has a hole, reduce the function to lowest terms to help you find the y-coordinate. All right? Okay, so once again, all of these examples are going to have answers here. Let's skip down and look at our g of x here. We'll take a look at this function. So if you're asked to figure out vertical asymptotes or holes in the graph, those come from excluded values. Excluded values come from division by 0. So we set the denominator equal to 0, and we solve it, either factoring, quadratic formula, whatever we need. Here we've got a 2x plus 1 times an x minus 4. We can set each of those factors equal to 0. Subtract the 1 divided by 2. Add the 4. Now, to figure out where there's a vertical asymptote or where there's a hole in the graph, I mean, we're going to dial this into Desmos here in a minute, but the way we can predict that and prove it algebraically is to reduce the function to lowest terms. So let's attempt to do that. Factoring the numerator. And you can see, sure enough, we've got a common factor. So this is the factor that cancels out. All right. So since the 2x plus 1 didn't cancel, we expect to have a, well, since it didn't cancel out, the graph isn't going to get smoothed over there. We expect to get a vertical asymptote at x is negative 1/2. Since x minus 4 did cancel, we're going to have a hole at 4 comma something. And how do we get that? Well, if x is close to 4, the x plus 3 over 2x plus 1 is going to be close to 4 plus 3 over 8 plus 1, which is 7/9. So we expect the hole there to be at 4 comma 7/9. So vertical asymptotes, holes in the graph, going to come from places excluded in the domain. Why? Those are the places where you're trying to divide by 0. If the factor causing the 0 cancels out from the denominator, good news. You just have a little hole in the graph there. To figure out where the hole in the graph is, you know the x value. Reduce the function, plug in that x value to get the y value. Just like we did before when we had holes in the graph. If the factor causing the 0 does not cancel from the denominator, then the graph is broken there. It's a vertical asymptote. So once again, you can predict all of this algebraically. And now what we're going to do is pop over to Desmos and confirm it graphically. But is there any questions on this part? You see how we're determining what's what? And in the case of the hole in the graph, how we're getting the y value. All right, let's dial this in. So that g of x will just be consistent here. X squared minus x minus 12 over 2x squared minus 7x Yeah, minus 4. We're looking at x equals negative 1/2 is supposed to be a vertical asymptote. And we can see that. That confirms it there. Boom, there's our vertical asymptote. And now when we get over near 4, there should be a hole in the graph at 4. Boom. Hole in the graph at 4. And it should be, the y value should be around 9/7. So let's look at what 9/7 looks like as a decimal and make a little table here with x1 and f of x1. And let's look at x getting close to 4 from the left and 4 from the right. So here's x coming into 4 from the left. That means we're looking at things a little less than 4, like 3.9, 3.99. And we can come into 4 from the right-hand side. And so x would be a little bit bigger than 4, like 4.1, 4.01. And so here's 9/7, 1.2857, etc., etc., etc. Let's see, as we plug in things a little less than 4, 3.9. Oh no. This is my g of x now. There we go. Wait, was it 9/7 or 7/9? Did I just goof that? 7/9. Well, that would help if I had the right target in there. 7/9. Boom. There's 7/9. 0.7 repeating. So we can see here as I get closer and closer to 4, the y values are getting closer and closer to 0.7 repeating. And if I come into 4 from the other way, I get the same stuff. Okay? So that graphically checks our answer. And once again, one of the big themes in this course is the connection between the algebra and the geometry. And that's why Desmos is very easy to work with, and it's free. Okay, so it's a great tool to help us investigate these functions. Okay, so rational functions, the new idea is, we're dividing now. We better not divide by 0. That can cause local issues with elements excluded from the domain. So vertical asymptotes, holes in the graph, we didn't see those things with polynomials. All right. End behavior is something we've talked about with polynomials. What does end behavior look like in rational functions? So let's go back to the 2 examples we've done. So we're going to break tradition here. Let's, I don't know what I'm doing all that for. Boom. Let's take a look at this this example here. We have it up on the screen here. Let's look at the end behavior of this thing. And remember what end behavior is all about. End behavior is all about what happens as x goes off to plus or minus infinity. So if we look at this, it seems to be flattening out, right? So that's a lot different than polynomials, because in polynomials, if we had an even degree polynomial, we would zoom out, it looked like a U shape, either both up or both down. If it was odd, it looked like an S shape. Okay, here it looks like it's flattening out to a particular y value. So let's figure out what that y value is by using what we know about polynomials. Okay, so when we looked at end behavior, I'll call it EB, we're looking at what happens as x goes to negative infinity and as x goes to infinity. Okay, the so-called ends of the x-axis. And what we learned in chapter 2 is that for polynomials, the leading term determines the end behavior. All right. So if I look at our function here, g of x, x squared minus x minus 12 over 2x squared minus 7x minus 4. And we look as x goes to, well, plus or minus infinity. We can use what we learned in chapter 2 to help us. Because in the numerator, the leading term in the numerator is x squared. The leading term in the denominator is 2x squared. So it stands to reason that as x goes to plus or minus infinity, the numerator is going to more or less look like x squared. The denominator is going to look more or less like 2x squared. And that simplifies to 1. Simplifies to a half. It looks like Kitty's back. Let's let her in quick. Okay. So as x goes to plus or minus infinity, the g of x should settle down to about 1/2. And remember, the g of x are y values. We're looking at the graph y equals g of x. That means the y values are getting close to 1/2. And this creates what's called a horizontal asymptote. Of y equal 1/2. So we had vertical asymptotes. Those were vertical lines that the function was trying to be like. Horizontal asymptote is a horizontal line that the function's trying to be like. So we're using the end behavior information we know about from chapter 2 and using that here. So let's confirm this graphically and numerically on our curve here. So that's why I went ahead and did this. So let's take off the x equals negative 1/2 and let's put in the y equals positive 1/2. Boom. And let's dot it, or dash it rather. So typically when you include asymptotes in the graph, you dash the lines because they're technically not part of the graph. They're just sort of guides on what's happening to the graph. And you can see as x heads off to negative infinity, as we head over to the left, the graph of the function is getting really close to the graph of that horizontal line. How could we see that numerically? So going off to negative infinity, we're looking at plugging in quote-unquote large negatives, meaning big numbers with a negative sign attached, so like negative 100, 1,000, 10,000. And notice what's happening to those g of x values are getting closer and closer to 0.5, which is 1/2. And the same thing will happen as we blast off to infinity. Getting closer and closer to 1/2. Okay, so that's how we can confirm what's happening here with the graphing utility. So hopefully you see the end behavior. It's the same concept in chapter 2, and we're using what we learned in chapter 2 to help us with it. All right, that's just kind of how math goes. Okay, so for example here, 6x minus 5 over 2x plus 1, we can do the same thing here. You've got the 6x running the show in the numerator, the 2x running the show in the denominator. So that gives you a quotient of 3. So as x goes off to plus and minus infinity, the function values are getting closer to 3. And that gives us a horizontal asymptote y equals 3. Let's take a look at this one together. Let's look at 3x minus 1 over x squared minus 25. I think that was it. Yeah, that works. And let's think about as x goes off to plus or minus infinity here, the r of x, well, once again, I look, leading term here is 3x, leading term here is x squared. Now that gives me a 3 divided by an x. So we're not getting a number, we're getting another function now. So let's think about what happens as x goes up to plus or minus infinity. What's going to happen to this? I'm going to have 3 divided by plus or minus big numbers. So we're going to have things like 3 over a billion, or 3 over negative 1 billion. 3 over a billion, that's going to be a very small positive number. 3 over negative a billion is going to be a very small negative number. Both of these numbers are pretty much 0. And so the r of x is going to be approximately 0, which means y equals 0 is a horizontal asymptote. Okay. Now, y equals 0, if you think about that horizontal line, when I graphed it on the xy plane, that horizontal line, y equals 0, is also known as the what? The x-axis. So when I graph this thing, what I should expect to see is this function getting closer and closer to the x-axis as we zoom out. So we're not going to graph, well, I guess we could do y equals 0. There we go, aka the x-axis. You notice we've got vertical asymptotes here at -5 and 5. Hopefully that makes sense because that's what's going to make that denominator 0. But we're not concerned for that kind of local behavior. We're concerned with the end behavior. And sure enough, as we zoom out, we can see that the graph is getting closer and closer to the x-axis. We can do the same thing we did before. This is the scientific notation. This means it's -0.13 zeros and a 3. That's pretty close to 0. And here we've got something positive, 0.12 zeros and a 3. So we can see that that's what's going on. So those outputs are getting really close to 0. Okay, so we've got vertical asymptotes, vertical lines. The function's trying to be like, they come from excluded values. The other case with excluded values are holes in the graph. When we look at end behavior, we can get horizontal asymptotes, horizontal lines. What's the last kind of line there is? There's vertical line, horizontal line, and then there's the increasing or decreasing or slanted lines. And so let's take a look at this particular function, h of x, on our graph here, x cubed over x squared plus x minus 1. Whoops, excuse me on that. Take that off there for now. Okay. Now, so once again, you've got some vertical asymptotes happening. But if I'm looking at end behavior, I'm zooming out. And as it zooms out, you see you got that slanted line there. So the question is, okay, well, what's causing that behavior? Well, let's do a preliminary analysis here using end behavior. So let's see. As x approaches plus or minus infinity, let's see what the h of x is going to look like. Well, there's only one term in the numerator, so that's the dominant term for n behavior there. In the denominator, there's only there's an x squared there as the dominant term. So when I do that, I get x. So let's graph the line y equals x and see if that's what the asymptote is, because y equals x is a line. It's a slanted line. So let's put in the y equals x. All right, and let's check it out. So what do you notice here? The graph of the function looks like a line, but it doesn't look like it's getting closer to y equals x. In fact, it looks like those two lines are what? If you were to describe those two lines, you'd say they look parallel. That means that they've got the same slope, except the y-intercept's different. And so the question is, I'd really like to know what that intercept is. So at this point, there's only one way to get at this algebraically, and that's actually going through the long division. What we could do here, just for fun, is we could add a slider. This is what's great about Desmos, is we can experimentally try to figure out what that is by using a slider. So if we move this around, we're trying to figure out which of these it's going to be so that they match up. So it looks like -1 would do it. Okay, so it appears as if here it appears as if y equals x minus 1 is an asymptote. Okay, and since it's a slanted line, we call this a slant asymptote. Okay, slant asymptote. But once again, how do we prove it algebraically? Okay, and in this particular case, the b that works is a nice friendly integer -1. What if it were some kind of crazy decimal or something? So the only way to do this is we do long division. Now back in chapter 2 we had synthetic division, and sometimes you can use synthetic instead of long division, but in general long division is going to be what we need to do. Let's review how that works. First off, you've got x squared plus x minus 1, and you're dividing that into x cubed. And you want to make sure all of the powers of x are represented so we can keep things lined up. So the divisor here, x squared plus x minus 1, all the powers of x's are represented there, but the dividend here, we're missing a ton of x's. So anything that's missing, you want to put a 0 in. And now we do the division. We look at x cubed over x squared, and that gives you x. So the x will go here, right? So I just take this divided by that. So x cubed over x squared gives me x, which is what goes there. And then what I do is I multiply through and then subtract. So x times x squared is x cubed plus x squared minus x, and then I'm going to subtract. So x cubed minus x cubed is 0. Great. 0x squared minus x squared is a minus x squared. 0x minus a negative x is a plus x, and then we bring down the 0. And now I take this negative x squared divided by x squared. And that gives me a -1. So that's what I get. Now I put there -1. Multiply. Negative x squared, negative x plus 1. Subtract. cancel out. X minus a negative x is a positive 2x minus 1. And so that's my remainder. Okay? So what does this mean? Okay, when you do a division, what does it mean? So once again, we kind of talked about this back in chapter 2 when we talked about division. This gives us another way to write our function h of x. But first off, are there any questions over the machinations here? So the claim is that h of x, which can be written this way, this is how it was given to us as a single fraction, we can rewrite this as the quotient x minus 1 plus the remainder 2x minus 1 over the divisor x squared plus x minus 1. And let's look at what's happening as x goes to plus or minus infinity to this part. So this is like the remainder piece. Leading term here is 2x. Leading term here is x squared. So when I simplify that, I get to 2 divided by x. And we've seen this before. As x goes to plus or minus infinity, that's going to go to 0. So this is going to head off to 0. And what's going to be left, folks? The x minus 1. Okay? So as x goes off to plus or minus infinity, the h of x is going to look like that x minus 1. And so that's how we get, algebraically, the slant asymptote, y equals x minus 1. And so we can see that on the graph. There it is. Now, vertical asymptotes are from excluded values in the domain. Horizontal asymptotes and slant asymptotes are end behavior. So whereas you can never cross a vertical asymptote with a rational function, because those values by definition aren't in the domain, you can see here that we cross slant asymptotes and you can cross horizontal asymptotes. You can see here, that my remainder is 2x minus 1. If I were to set the remainder equal to 0, you would get x equals a half out of that. And sure enough, that's exactly where we cross the asymptote, is at x equals a half. So when the remainder is 0, the function and the asymptote are the same. So there it is. Okay, so there's that. So those are the 3 types of asymptotes you can get: vertical from excluded values, horizontal and slant from end behavior. And pretty much every single college algebra book breaks this down into cases. Now, if you kind of follow what we did and understand what we did, you don't need to memorize these things, but this is the long and short of it. So this is kind of the summary here. Horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will be y equals 0. If you have a larger power of x in the denominator than the numerator, the denominator overwhelms the numerator and takes the fraction to 0. If you get the same degree, then you can just look at your leading coefficients to get your horizontal asymptote. If you have your rational function and the degree of the numerator is exactly 1 more than the degree of the denominator, like in our last example, we had an x cubed over an x squared, then you're going to get a slant asymptote. And in order to get excuse me, the formula for that, you need to do your long division. Okay. So let's run through these here. Once again, we're looking at horizontal or slant asymptote. Horizontal, slant asymptote, these come from end behavior. All right. So we always look as x is going off to plus or minus infinity. We look at our f of x. We always look at the leading term in the numerator over the leading term in the denominator. In this case, that simplifies to a half. So that means that we have a horizontal asymptote, y equals -1/2. And we can check that on Desmos to make sure that that's all legit. If I look at what's happening here with g of x, the leading term is the only term in the numerator, 5x. Leading term in the denominator is an x squared. Notice there's more powers of x in the denominator than the numerator. That means that when I divide, I'm going to be left with factors of x in the denominator that are going to blow up. As x goes to plus or minus infinity, you've got 5 over some ridiculously large number. That's going to go to 0. And so we get a horizontal asymptote, y equals 0. Are there any questions on these two examples? And last but not least, let's take a look at r of x here. As x goes off to plus or minus infinity, let's look what's happening with the r of x. The leading term in the numerator is the 2x cubed. The leading term in the denominator is x squared. Well, that simplifies to a 2x. So we had exactly one more power of x in the numerator than denominator. This tells us we're going to have a slant asymptote. Now the slant asymptote will look like a 2x plus a b. The only way to get that b is to do the long division. So we're missing an x here, so we'll put the 0x in for there. We're missing a constant term, we'll put in a 0 for that. And then we do the division. 2x cubed over x squared. That gives me 2x, so there's the 2x there. When you multiply through, 2x cubed plus 0x squared plus 2x, and now I subtract. Those cancel out, so I just have a 0x and then a 0. I take minus x squared over x squared, give me -1. Boom. That's my slant asymptote, is 2x minus 1. Whoops, don't want to put that there. Okay, whoops. And once again, I really encourage you to check these with Desmos. Graph the function, graph the asymptote, zoom out, and see that it's doing what it's doing. Okay. All right. What I would like to do is I want to save this example for Thursday. So Thursday's lecture, you can think of today as Introduction to Rational Functions. What kinds of things can happen? All right. We got local behavior, domain issues. We've got end behavior stuff. Thursday, we're going to just redo all of this and put it all together. So Thursday, we're going to take everything, put all the pieces together and make graphs. I want to hold off on this example because this example works that stuff backwards. And I think before we work backwards, we need to get good at working forwards.